Hi, everybody. Today we're going to talk about stoichiometry. Stoichiometry might seem very daunting, especially in your chemistry class, but it is just as easy as making a sandwich. So let's dive in. Just to kind of for a little bit of background, for a simple example of how stoichiometry actually works, let's talk about making a sandwich real quick. This is the recipe that we're given, or if we combine one tomato slice, two bread slices, one cheese slice, five turkey slices, and one lettuce slice, we can create this one specific sandwich. We have to follow this rule exactly now the cool thing is we can actually get conversion factors talking about from the reactant to the product, like in chemistry, where for example here, two bread or two slices of bread makes one sandwich. And the same thing with five turkeys or five slices of turkey or makes one sandwich as well. And this is important, especially when we get to the next slide. Now, how many sandwiches can we make with these specific amount of materials? Where we have 7 tomatoes, 12 pieces of bread, 6 pieces of cheese, 25 turkey, and 6 lettuce. Now, it might take a minute to actually go through this, but it's very intuitive that we can actually only make 5 sandwiches. And you have done this math in your brain. And that is because we do some counting. If we have 7 tomato slices and we use one for every sandwich, we can make 7 sandwiches total with all of the slices of tomato. And if we go through and count every single thing along with their recipe, 25 turkey slices makes 5 sandwiches, 12 bread slices makes 6 sandwiches, 6 cheese makes 6 sandwiches, and 6 lettuce makes 6 sandwiches. These are the amount of sandwiches that can be possibly made, maximum with each specific reagent. But we can only make 5 sandwiches. And that is because if we look at the turkey slices, what this means is that after 5 sandwiches were made, all of the turkey slices will be gone, and you cannot make any more sandwiches. So turkey in this case is our limiting reagent because it will run out first before more product can be made, or the reaction stops there. Now, relating this back to chemistry, it's the same idea with the idea of counting. Now, let's relate this to a chemistry and stoichiometry problem. How many water molecules, or H2O, can be formed with 11 molecules of H2 and 4 molecules of O2? So, like before with the sandwich recipe, this is our recipe. 2 H2s and 1 O2 will be combined together in order to form 2 H2Os. That is the recipe for this specific chemical reaction. And with it, we can get specific conversion factors like we did before for reactant and our product that we're going to be looking at. Where 2 molecules of H2 can make a maximum of 2 molecules of H2O. And the same thing with 1 molecule of O2, we can actually make a maximum of 2 molecules of H2O. These are the conversion factors necessary that we read from our recipe or chemical reaction. And this reaction has to be balanced. So that's what we're going to see on the next slide with the next problem, but you have to make sure it's balanced before you start any of these conversion factors. With these conversion factors, we can convert from the molecules that we do have into the molecule of our product that we're going to be looking at. So if we want to convert to molecules of H2 to molecules of H2O, this is what we would do, where we would have 11 molecules of H2 with our conversion factor from H2 to H2O to give us that we can make 11 molecules of H2O, maximum with our H2 reactant. And if we do the same thing for our O2, we have 4 molecules of O2, and we can see we can make a maximum of 8 molecules of H2O. Now, this is where you have to intuitively understand what this means. And this means a maximum of 8 molecules of H2O can be made because O2 will be fully consumed after 8 molecules of H2O was made. O2 will be completely gone. And so O2 is the limiting reagent or limiting reactant, depending on your definition. And this means 8 molecules of H2O will be made. That's answering the question. And you find it because O2 is our limiting reactant or it's going to be completely gone. Now let's look at a little bit of a harder one. You won't be really dealing with molecules all the time, and you might be dealing with grams because that's what we actually measure with a scale in chemistry lab. What is the maximum amount of CO2 that can be produced from the combustion of 4.09 grams of propane, or C3H8, and 8.84 grams of O2, or oxygen gas? Now, if you need to be reminded of what a combustion reaction is, it's going to be our hydrocarbon reacting with our oxygen gas, forming carbon dioxide and water as a product. Now, like I said before, these reactions need to be chemically balanced, where we have the same number of elements on the both side of our reaction arrow. So this is important. So if we go through, To balance the specific chemical reaction, we're going to look at for elements that are on both sides, but only in one specific compound. So for on the left, we have 3 carbons. So if we put a 3 in front of our CO2, we'll balance it out having 3 more carbons. And we're going to move on to hydrogens because oxygens are a little bit more complex. On the left side, we have 8 hydrogens. On the right side, we only have 2. So if you put a 4 in front of the H2O, that'll balance out the hydrogens on both sides. So our carbons and our hydrogens are balanced. So now we need to balance our oxygens. On the right side, we have 6 plus 4, so we have 10 on the right side, and we have 2 on the left side. So if we put a 5 in front of our O2, our oxygens are now balanced as well. All of the elements are now balanced, and now since we have a blank in front of our C3H8, this usually just means a 1. So that we're going to fill it in with a 1 as well. Now this is important because now we can get our conversion factors that we may need. And so for example, 1 mole of C3H8 is the same thing as saying 3 moles of CO2. And the same thing with 5 moles of O2 can make 3 moles of CO2. These are the conversion factors that we're looking for the calculation that we'll need. And the reason why we use moles and not grams is because grams is a unit of mass, while moles is a unit of counting. And we can only make these relationships with our recipe through counting, not mass. So you can say 1 molecule is equal to 1 molecule depending on the coefficients in front of a recipe. And you can say 1 mole is equal to 1 mole depending on our coefficients again. But you can never say 1 gram of a specific substance is equal to 1 gram of another substance. Keep that in mind. This is a mole ratio. So we actually need to convert all of the given amounts to moles in order to use these specific conversion factors. So a lot of the times we'll be given grams, but you have to convert it to moles in order to actually use these ratios. And with the molar mass, this is what you'll end up finding after you find the molar mass using the periodic table, where CO2 has a molar mass of 44.01, O2 32, C3H8 44.10 grams per mole, and we'll use this within our specific calculation as well. Now, in order to determine the maximum amount of CO2 that can be produced, we're going to see the maximum amount that can be made from each individual reactant. So let's do that. Let's look at the top line first. We have 4.09 grams of propane. And if you want to go through the calculation a little bit more in depth, we'll have a practice solving video in the next video. This is more just for introduction of stoichiometry. But what we can end up doing is using our conversion factors of our molar mass and our mole to mole ratio, where if we convert from grams of propane to moles of propane, and then moles of propane to moles of CO2, we see we can make 0.278 moles of CO2. And we do the same thing for O2. We see that all the oxygen gas can make 0.166 moles of CO2. This is the same idea now. We can see how much they can both maximally make. And so once 0.166 moles of CO2 is produced, our oxygen will be completely gone. So O2 is our limiting reagent. And to answer a question from our slide here, the maximum amount that can be produced is 0.166 moles of CO2. We convert that to grams if we ended up using the molar mass, but this problem doesn't ask for that, so you can always say 0.166 moles of CO2. Please like this video, and please subscribe for more chemistry and math related content.